Alright, welcome to another AQA AS Chemistry video. We're now on the second topic for AS Organic regarding halogens. So halogens has 3 topics. We've done group 2 already, we've done periodic table. So there's only one more video after this, and then I'm pretty much done for, inorganic chemistry, and more importantly, we're done with all of AS chemistry in 2 videos time. So this video, and the next video, and then it's done. This is quite a lengthy video. I'm considering whether or not to chop this down into 3 videos, but I'll see at the end of this, but I'm going to try to do it in one video. Alright, so reactive trends of the halogens. So the redox abilities of halogens change within the group, and these can be used to identify halide ions. So the oxidation reaction. So oxidation is the loss of electrons, as you remember from oil rig. Fluorine is the most oxidizing element because it's the most electronegative. So an oxidizing element in itself is being reduced, because remember, fluorine in itself is going to be reduced. If it's a good oxidizing agent or oxidizing element, it means it oxidizes other compounds, and in itself is being reduced because fluorine, as I said before, is the most oxidizing element. Remember the definition of electronegativity is the ability to attract a lone pair of electrons. Is the ability of an atom to attract a lone pair of electrons in a covalent bond, and that's what it's able to do, and it's the best at doing that. So if it's able to attract electrons, it's in itself very good at being reduced, and it's good at oxidizing other compounds. And the trend in oxidizing ability follows the trend in electronegativity. It decreases down the group. So like the trend in electronegativity, it's the same trend for the oxidizing ability. They follow this. They go hand in hand. Reduction reaction. So reduction reaction is the opposite of oxidation, and it's the gain of electrons. So the trend in reducing ability is the reverse of the trend in oxidizing ability. So then, in that sense, iodide ions are the most reducing. Iodide, in that sense, they're the best at being oxidized. So wait, is that true? Yes, they'll be the best at being oxidized. They're the best at reducing other compounds, because iodide has a very, as I said, is not very electronegative, very large ion, so it has a very weak first ionization enthalpy, and very easy to remove an electron from its valence shell, and therefore it's very good at being oxidized in itself and reducing other compounds. And obviously fluoride ions are not reducing at all. It's very difficult to remove an electron from a fluoride ion. Alright, so halide displacement reaction. So if an element halogen is added to a halide solution, the heavier halide will be displaced. So this is because the lighter halide has a greater preference to the halide ion because it's more electronegative. So if you had CO2, if you added CO2, for example, or CO2 gas to a solution of sodium bromide, the chlorine would displace the bromine as a gas. I'm going to show you here, right? So this is just a table. I've copied this from Inorganic Chemistry, but if anyone just say go watch his videos, because his videos are much better than mine. But I copied this table, and I think it was a very good table because it explains it the best, right? It's just the smaller ions have a very high charge density and are very, I wouldn't use charge density in this case, but they're more electronegative, right? More electronegative. They're very good at they're very good at they're very good oxidizing agents, and therefore they're better at, if the smaller ions are better at I say ions, the smaller atoms really, F2 in itself, are better at would we be reducing? I have to be careful with my wording here. They're better at, the smaller atoms are better at oxidizing larger ions. Yes, yeah, they're better at oxidizing larger ions. As they're because they're electronegativity. So here I've got an example, right? This is a table, so you've got your ions here. Obviously, you don't get ions by themselves. It'll be, it has to be an ion in an ionic compound, always in solution. And then you have your atoms here: F2 gas, CO2 gas, Br2 liquid, and I2 solid. F2 is a pale yellow, CO2 gas is like a pale green. Bromine is like an orange. You should remember that from doing addition reactions. Remember, for testing the presence of an alkene, you should know that Br2 or bromine water is orange. And I2 in solution usually is found as a purple solution, and I'll show you why it's in solution. It has different colors, but for solution it's a deep purple, and I'll show you why. So this is one way we could identify what ions we have, by doing displacement reactions. Obviously, this potassium here would just be a spectator ion. But let's say you had F2 plus 2 Kc. Actually, no. F2 plus potassium fluoride. What would that form, right? Now, that would just form F2 and then potassium fluoride again, because they have the same reducing ability. So it wouldn't have any. They would form the same thing again, and it's just like, there's just no point. I mean, it's nothing really happening there. However, if we go down to say F2 plus 2 KCl, because F2 is better at, be careful with what I say here. It's better at oxidizing, there we go. But since F2 is better at oxidizing than potassium, better than the Cl minus, it's gonna displace the Cl minus ion here from potassium chloride, and it's going to form potassium fluoride. It's going to be reduced, right? It's going to be going from, essentially what's happening here. Oh, I don't want to use it on there because it's F2 going to form 2F minus plus 2E. No. F2 plus 2E minus goes to form 2F minus, and then the Cl, 2Cl minus, goes to form Cl2 plus 2E minus. And that's what's being able to happen here. There's other things when you get to year 2, when you know about like reduction, electron potentials and all that, but for the sake of the fact of just knowing this here, all you need to know is that F2 is better oxidizing agent, and is therefore better at oxidizing the Cl minus, and in itself being reduced. So in this case, if you have this reaction here, balanced here, F2 plus 2 KCl goes to form 2 Kf, or potassium fluoride, plus Cl2. Now I want people to try and do the rest of these, right? And if you're having time, you can probably do them quickly. If you want to do that, that's fine. But I'm gonna just quickly go through them here. So with this, it's very easy to see that this would work, right? So F2 is better is smaller than Br, so it's better oxidizing agent. So you'd form 2kf plus Br2, and then 2kf plus I2, right? Now, would this work with Cl2 and Kf? No, because Cl2 is bigger than a fluoride ion, and therefore it wouldn't be a better oxidizing agent, and therefore you'd have no reaction in this case. And then you can see here Cl2, KCl, same oxidizing ability, no reaction here. But Cl2 is a smaller ion than Br minus, so Cl2 is a bigger atom than Br minus, and therefore it will be better. It's better at oxidizing. It's a better oxidizing agent. So it's a strong enough oxidizing agent for this reaction, right? And then you'd form 2 KCl. My handwriting is terrible. And what the hell is going on in this? 2 KCl plus Br2, and then 2 KCl plus I2. Now I think you can see the trend here, right? You know for a fact that if that is Br2 is not bigger, is much bigger than a fluoride ion, and Br2 is better than Cl. So that's going to get cancelled out, and it's the same principle for all these. In fact, I2 is such a weak oxidizing agent. It can only really oxidize acetine. I didn't bother to go down there, but you can see the pattern here, right? And yeah, so Br2 would only be able to oxidize potassium iodide, and then you would form 2 KBr, potassium bromide, plus an I2. Now, why I say this, why I say this is important, right? Why this is a good test, because in your products, you're forming CO2. We know CO2 is pale green. So we know if we didn't know what this solution was, right, and we added F to it, fluorine gas to it, and all of a sudden it goes from being whatever color it is, colorless, to forming a pale green gas, then we know that CO2 is present, and our original compound was so and so. But we know that CO2 is present, and the same for here. If it turns orange, originally we had potassium bromide, and then in solute, iodide is like usually it can be grayish usually as a solid, but then as a solution is deep purple. And remember what we said, these ions, these this wouldn't form a solid. This I2 is actually dissolved in a solution, right? Because we're using a solution of potassium iodide, and we're bubbling through this F2 gas. And so this solution would be, you have I2 but in solution, and in solution I2 is deep purple. And the same principle here. This would be orange because we have Br2, deep purple again, deep purple. And the reason, as you go up, as I said before, the better the oxidizing agent. So now that's one test, but you can see here, it's not the best test for all of these. All of these kind of get cancelled out. You can't really test for these. So it's a good test to an extent, but there's other ways you could test for the presence of halides. Another way is using reactions with sulfuric acid, right? Halides react differently with sulfuric acid depending on their reducing ability. So reactions with fluoride or chloride produces HCl or HF. Reactions with bromide produces Br2 and some SO2. Reactions with iodide produces I2 immediately and will reduce the sulfur to H2S, which is a toxic molecule that kind of smells like rotten eggs. All right, so again, I've stolen this from Allery Chemistry. His videos are too good. I can't, sometimes you have to bow down to the goat. But it is a good table, and it's good that it's what I use in the exam whenever I get this. This question always usually comes up, and it's a question of they'll tell you to write a balanced equation for or at least an ionic equation. You can get away with an ionic equation regarding a halide with sulfuric acid. Now, one thing you need to know is that you form one of three things, right? So let's say you have H2SO4, and you had, these are going to be, obviously, I say it as the ions, but it'll be NaI, sodium iodide, sodium bromide, sodium fluoride, or sodium chloride, right? You'd form either, depending on their oxidizing ability, depending on their oxidizing ability, the ability to oxidize, is that ability to oxidize? Their ability to, it'll be their reducing ability. Depending on their reducing ability, because they're reducing the H2SO4, right? If they're reacting with H2SO4, in themselves they're getting oxidized. Yes, definitely they'll get oxidized because they're the ions anyway. Yeah, depending on their reducing ability, they'll cause, they'll form different products. So it will form NaHSO4, SO2, S, so sulfur or H2S, right? And they all have, they can form more than one product, but they have different reducing abilities. Why? I minus as you go down the group, as we said before, as you go up the group, they become better oxidizing agents, but likewise, as you go down, become better reducing agents, right? I'm not going to write that down because it kind of complicates it there, but better reducing agents as you go down the group. Why is that? Because ionic radius increases, electrostatic attraction between and there's also more electron shielding, and the distance between the nucleus and the outermost electron further away. There's a weaker electrostatic attraction between the nucleus and outermost electron, and so it's much easier for that outermost electron to be released, and hence why you can see there's a lower first ionization energy. But you already know this if you watch my previous videos. But that's why they're better reducing agents, right? Or better reducing agents. They themselves are getting oxidized. Iron, as you see here, and you can see the trend here. Chloride is not the best reducing agent. That's why I can only go up to sodium hydrogen sulfate. Br minus is a better reducing agent, and then because it's able to reduce a bit more, and I minus is the best, well, second best, I guess, after acetine, right? But in this group, would be the best reducing agent, and you can tell reductions it's having because there's a changing. These numbers here represent the oxidation state of the products. So if we know that the oxidation state of sulfuric acid is H2SO4, if you didn't know why. Remember, I already made the video explaining how to work out oxidation states, but in case you haven't got far all the way to that part, in case you've got this far without knowing, I'll say right here, right? So we know that hydrogen is always 2, or 1, so hydrogen is always +1. We've got 2 of those, that's 2 there, plus, let's call that X, and oxygen is always -2, so we've got 4 of those, so that's, -8 really. And then the overall charge of this is 0, so the overall oxidation state is 0. 2 plus x -8 equals 0. X is equal to -6. 0, x is equal to +6. Therefore, the oxidation state of sulfur is +6. So that's the oxidation state of sulfur at the beginning, right? So first we're going to have your first reaction, right? And that's with fluorine or F minus or sodium fluoride and sodium chloride, right? So it'll be H2SO4 plus, so you can just do the straight reaction. It's H2SO4 plus NaCl goes from sodium hydrogen sulfate, that's what this is called, plus HCl, and it also form, and if you're doing it with F minus, right, have the same kind of reaction and form it would form hydrogen fluoride instead. You just change this around. In this reaction, if they ask what you see, obviously you're forming HCl, but it's HCl gas, right? And that's a white misty fume, and it's also very acidic. So you kind of do this reaction within a fume cupboard. If they ever ask, so it's just. I say these things because in an exam they'll say things like, "What can you see from this reaction?" And they'll ask a question like, "What can you observe from this reaction?" Or okay, actually, I'll say the whole thing, right? They'll say something like, "Write the balanced equation for this reaction between sulfuric acid and sodium chloride," and then they'll say, "Write any observations and write any safety precautions." You can get a question like that, right? And to break that down, you break down the first thing. Write down your equation. Is it balanced? That's another mark. What's my observation? White misty fumes. And what's the safety precaution? If we're talking about safety precautions, what is the thing that I have to be worried about? And then what should I do about it? There, 5. And then that's kind of why it's important to kind of know these things. Another thing to notice about this is that if you can see here, remember our oxidation state of sulfur, right? Or of sulfuric acid, the sulfur in sulfuric acid is +6, right? And we're forming sodium hydrogen sulfate, because remember we said it's not that good of a reducing agent. But sodium hydrogen sulfate is also +6, right? So then if there's no change in oxidation state, this reaction, there's no reduction actually happening here for the sulfur. So therefore, this isn't actually a redox reaction. There's no reduction actually happening here. And this is just a straight reaction, no redox occurs. However, if you go to the next reaction, right, you can see here, so for example, the next reaction is a reduction because it's going from +6 to +4, right? And I'll go through it here, right? So what's actually happening is that your Br minus is being oxidized because it's a good reducing agent. It means it's reducing another compound. And let me actually just write out for you. Go through it right here. so you can kind of see what I would go through if I was doing it myself, right? I would say H2SO4 plus Br minus. How am I gonna get through this, right? How am I gonna forget? Oh, I'd write this in the ionic way because that's for me how I do it. But you can just do it straight if you want to do sodium bromide. But I'd separate them out. So I'd say, how do I? Well, I know bromides. I know the bromide ion is being, because remember the sodium ion is a spectator ion. I know the bromide ion is being oxidized, right? So I go from Br minus, and I'm forming Br2. So this must be 2 Br minus. I need to balance the charge, 2 electrons. Right. I am going from H2SO4. Some people get really like kind of, you know, they feel uncomfortable doing these things. Just look at what you have, right? Look at this is how I'd write it out. If they ever ask me how to write that out, right? They'll say sodium bromide, but you can just do the ionic equation. So if they ever ask me how to go from H2SO4 to SO2, this is how I'd write it out. So I know in my reactant side I have H2SO4. And I know in my product side, actually it's kind of big. Do I really need to write that big? But at this point, man, who cares, man? I have H2SO4 on this side, and I know I'm forming SO2. You know it's SO2. Just look at what you have, and you should remember how to balance equations. I don't think I've done the video about how to balance equations, but I think it's from GC. You should know this by now, or watch a video from Alloy Chemistry. Will probably explain it better to you. I'm probably not going to go through that, but if you know that, you know, if you know how to balance equations, right? Just think, there's 2 oxygens here, and there's 4. I always balance the oxygens first, right? I need to have 2 more water molecules here because there's 2 more oxygens here. I can only have balanced oxygen by water. The sensible thing to do first is by water. So I have 2 H2Os. But now I have 4 hydrogens here and 2 hydrogens here, 2 H plus. But now I've got a 2 H plus charge. I need to balance it because there's no charge on this side. 2 electrons. But now you can see here, I've now shown that this is an oxidation reaction. So I have I've shown an oxidation reaction and I've shown a reduction reaction, hence a redox reaction. The 2 half equations are here. What do we do when we have 2 half equations or 2 redox half equations? We can combine them together to get one full equation. The electrons on both sides are balanced, so now I can just combine the 2. H2SO4 plus 2H plus plus 2 Br minus. Remember, you don't have to write down the electrons. Goes to form Br2 plus SO2 plus 2H2O. Alright. And that's it. There is also, you can write down the actual equation, which would be 2 sodium bromide, right? Yeah, if you have that, then it's 2 sodium bromide plus H2SO4 . Or really, if you have 2 H pluses here, right, it would technically be 2 H2SO4 actually. This is the non-ionic equation. And that will form Na2SO4 plus Br2 plus SO2. That starts the same. Br2 plus 2H2O. I like doing it like that because like you can see this, and I know some people can see this much, but I always like doing writing the 2 half equations, then write out the equation because I can just see it personally. But if you want to do your own way, by all means do it that way, right? Pause the video now, and I want you to try and do it for sulfur. Do the reaction between sodium iodide or just the iodide ion with sulfur and to form sulfur and to form H2S. Do those separately. And yeah, that's it really. You can do it with the SO2 if you want to, but I think you can already tell what I was going through when I've already did that. So do it with the sulfur and H2S. Bearing in mind, right, that iodide could form sodium hydrogen sulfate. Bromine could form sodium hydrogen sulfate. That's why I've kind of dotted it here. But that's the actual redox reactions. Actually, you know what? One thing they may actually say, right, in your reaction is that show a redox reaction between sodium bromide and sodium iodide, and it's a trick question, just showing you that you can only do. It's just showing that you understand what redox reaction is, and that it's just saying any product that's from here onwards, SO2S or H2S. If you do any product that forms sodium hydrogen sulfate, because there's no change in oxidation state, or sodium or Na2SO4, that's not a redox reaction. It's showing you don't understand what a redox reaction is. So just bear in mind that this first one here isn't a redox reaction. But anyway, yeah, pause the video now and then do this. Do the reaction between I minus and H2SO4 to form first sulfur and other one H2S. Right, I'm going to assume that you've done that by now. So if I'm forming just sulfur, right, so H2SO4, and I'm forming, I feel like I'm just making myself, I'm getting myself enough space when I do these things. H2SO4 forming sulfur. Right, so I've got 4 molecules of water. That's instantly because I have to balance the oxygen. So plus 4 H2O. I now have 8 hydrogens and 6 and 2 here. So I need 6 more H pluses. So plus 6 H plus. Balance the charges, plus 6 E minus. And then for the sake of iodine, really, 2 I minus going to form I2 plus 2 minus. Combine the 2, but remember, you have to look again at your, actually, yes. I wasn't wrong. Yeah. I thought I done. I didn't balance the first one here, but the reactions are correct. Yes. No, but for this one here, it is a redox reaction. We can combine them two, but the reactions aren't the same. So what we're gonna do here, we're gonna times this one by 3 to get the same number of electrons. Because if I times this by 3, it's easier to get 6, and we have the same number of electrons. I could divide this by 3, but then, let's not complicate things. Times this by 3, right? So that'll be what? 6I minus 3I2, and then having 6 electrons here. And now, obviously, on your exam, just times it separately. I'm just showing because I don't have enough space here, but we now have the same number of electrons. We can just add these two together now. H2SO4 plus 6H plus 6I minus, and that goes to form sulfur plus 4H2O plus 3I2 and that's it, really. Yep. And then I'm going to define one. Guys, by the way, I just want to say, if you feel like you want to go skip ahead, just skip ahead. You know me. I just go through everything so that in case people don't understand. But if you want to skip ahead to the next part of the video, do so gladly. I just want you to, if anyone needs help or is stuck, that's why I'm just doing these videos. So next one is to form H2S. So that's just out of my memory. So yeah, it's the same thing. So H2SO4, same principle. I always write down, always put a bit of space here because you never know, because you're gonna have something here but you don't know what exactly it is. So just leave that little bit of space there. Until if you've noticed, if you know if you've done this enough times, you just already know the reaction, and sometimes it's useful to actually just know these off by heart. And you don't have to learn them. Just you do them so many times. You do this exam question so many times, you just remember them. So when it comes to the exam, you just save so much time. You can just go and, because this question might come up, right? Write it down, and you just save yourself 3 extra minutes you could use to answer a much more difficult question or to review all your answers at the end of the exam. Anyway, I'm going to stop talking now. So that will be plus 4H2O, right? We have two H plus 2H2s here. Actually, no, 8, that's 10 electrons here. We also have plus 8H plus as expected, and plus 8E minus. And then it's the same as the last one really in terms of the fact that it's, sorry about that, 2I minus goes to form I2 plus 2E minus, times this by 4 to get, because we obviously have, we want the same number of electrons, so no, sorry, that's bad, that's wrong. 8I minus 4I2, 8 electrons, and then put the two together. I think I've done that correctly. Yes. I remember this because this came up in the exam, and I remember this came up in the exam, and I kind of regretted after I was talking to a friend of mine, and she said she answered actually the question correctly, and I thought I answered because I rushed. The question asked in the exam, which compound forms a solid. I think it said what I think it was either solid or just, yeah, it forms a solid compound, and I forgot. I just rushed there and said, because it was regarding iodide, which iodide compound reacts with H2SO4 forms a solid, and I neglected the fact that I just rushed through the question. I think I put down H2S or SO2, and then I just needed to put this onto here. So just take time, read the question properly. Sulfur is a solid. H2S is a gas that forms. It kind of smells like rotten eggs. SO2 is also a gas. Not a redox, but I think that's also. I think that's no. I think that's a gas. Yeah, I'm pretty sure that's a gas. Yeah, but sulfur is most definitely a solid. So they actually drop these little things in, so especially towards the end of the exam when you may be a bit tired and your concentration levels are a bit low. But yeah, be careful about these type of things. Have you noticed something here, right? You're going from +6 to +4, difference of 2. You're increasing by 2 electrons. Going from +6 to 0, 6 electrons. Going from +6 to -2, 8 electrons. It's just something that you may know. But anyway, next part of the video, identification of halides, right? So so these two I said before. So reaction with sulfuric acid and displacement reactions are 2 ways that you can identify halogens. The third way that you should know is by identification of halides. We can determine which halide ion is present for specific reactions, and we can, the reaction that we do is with silver nitrate. So first we would add nitric acid to the solution to prevent anomalous results. We don't want to have any what's the word I should be able to say, waste products, right? Waste products, unwanted precipitates. Yeah. So we add nitric acid before adding our sulfur nitrate, because the nitric acid reacts with and removes other ions that might also give a confusing precipitate with silver nitrate, and that's the definition by Chem Guide there before someone gets onto me there. But that's what it does, right? All the nitric acid does when you add it to, you have 3 test tubes, right, or 4 test tubes, right, and of your ionic salt. You'd add your silver, so you add your nitric acid first, to make sure that if there's any carbonates in there or hydroxides, soluble hydroxides, that prevents any Um, so we add dilute nitric acid first to remove any soluble carbonates and hydroxides. These could react with silver nitrate to form insoluble um, silver carbonate or silver hydroxide, and that would give and they kind of look like a certain white color, and that could give a false positive. It could get, so we call that a false positive result, and that's what we want to avoid, right? So if we add silver nitrate to a solution, so that after we do that, we add silver nitrate to a solution of halide ions, and the halides will react with the silver cations. So you have Ag plus, X minus. The X minus represents the halide to form AgX solid. So this is an aqueous solution to form precipitate here. The precipitate is shown by this little mini S here, because it's a solid, right? Test results. So the product of the silver nitrate reaction is a solid. We call this solid the precipitate. The color of solid depends on the halide which is involved. So we could have AgCl, which is a white precipitate, AgBl, which is a cream precipitate, and AgI, which is a yellow precipitate. And using silver halide products, we can test their ability to redissolve in ammonia. So after we do this reaction, we could this is what we get here, and this is actually enough to suggest what compounds we have, what initial. It tells us what compound we have, and if we know what the compound, if we know it's AgCl, we know that the original halogen was a chloride ion, right? But the reason is that we do sometimes do further testing because it can sometimes be a bit hard to tell the difference between a white precipitate and a cream precipitate, and sometimes the cream and the yellow precipitate. So one thing that it's kind of subjective to an extent unless you do colorimetry. But the one thing, colorimetry can be a bit long. The one thing that you can do is just do further testing, and by that you'd using the silver halide products, we can test that their ability to redissolve in ammonia. So you can add different concentrations of ammonia to each solution of the silver halides, and they would dissolve based for different concentrations. So AgCl should redissolve in dilute ammonia solution. Sodium bromide should redissolve slowly in a concentrated ammonia solution, and silver. Did I say sodium? I meant to say silver chloride. Silver chloride should redissolve in dilute ammonia solution. Silver bromide should redissolve slowly in concentrated ammonia solution, and silver iodide shouldn't dissolve even in concentrated ammonia solution. So first step one, as I said before, add dilute nitric acid to each test tube to remove any soluble hydroxides or carbonates that could react with silver nitrate, forming insoluble silver hydroxides or silver carbonates. Step two is that we would add silver nitrate to each test tube, and there's a formation of a precipitate. And so let's say this reaction here, right? If they asked, they might ask you to write out the equation, right? Of say for this example here, right? We're using potassium fluoride, and potassium fluoride as it is because you can't have the halide by itself, plus the silver nitrate that gets added, we would form. Remember, AgN going for silver nitrate plus your halide to form your silver halide plus NO3 minus. Ag silver fluoride plus H or potassium nitrate in this case. You can write it as the ionic equation, but if you wanted to do it like this, we could always do it like that as well, no problem. Now, the one exception to this is that we kind of disregard the fluoride, because the fluoride ion is so soluble, it will just redissolve back. As soon as it forms this, this doesn't really exist in solution really. It would just redissolve back into sulfur and fluoride again. And so, yeah, we'd kind of disregard that one. It's usually between the chloride, the bromide, and the iodide. And the chloride would give you, once you form, I think you can already kind of see what's here. You'd form AgCl from, if you have silver nitrate and a chloride ion, that's a cream precipitate. So that's a white precipitate, sorry. White precipitate. can just write PPT. In your exam, don't write PPT. In mark schemes, it will show PPT to represent precipitate, but don't write. They always say as well, don't write PPT, write precipitate. But I'm just trying here to show that it's, you know, shorthand. AgBr, which is a cream precipitate, and silver iodide, which is a yellow precipitate. As I said before, this can be very subjective. These colors can be kind of subjective per person, but what isn't subjective is when you see it literally being dissolved in its solution. So the step 3, which would be to add dilute ammonia. First, we add dilute ammonia solution to each test tube, and we should see that the silver chloride would dissolve first. Actually, it would redissolve again, and to be just a colorless solution. But AgBr and silver bromide and silver iodide shouldn't redissolve. So then after that, so if we see this redissolve, we know that this must be AgCl. That's enough information to say that is AgCl in there. And if you want to go back and say, therefore, Cl- was involved, so and so. But if it doesn't redissolve, you can't say that this is AgBr because it could dissolve be silver iodide. So to prove which one is silver bromide, we then add concentrated ammonia. Step 4, add concentrated ammonia solution to each test tube. And at this point, if that test tube, one of the test tubes now redissolves when you had concentrated ammonia solution, we now know that the one that redissolved in concentrated ammonia solution must have been AgBr. And if the AgI it doesn't redissolve, the reason why it wouldn't silver iodide doesn't dissolve at all. The reason why is because silver bromide and silver chloride have mostly ionic character, whereas silver iodide actually has some covalent character, which makes it quite insoluble, and so it wouldn't dissolve in an ammonia solution. And yeah, that's it really. Hopefully this video was helpful. If I just over talked too much, then just let me know in the comments, but hopefully this video was helpful, and that's it.